is everybody? Bye. Okay. Okay. So you are good now. We will release homework tonight. So hopefully it will be okay. So if you have questions about the homework, please just ask immediately, because I don't know how homeworks normally work actually. So the homework may be good, it may be bad. So just let us know, and we will change things very quickly if anything is wrong. So I think that's the only thing. Oh, the schedule, right? Because our schedule is very irregular. Well, we'll just make a web page with all the times. I think it's very regular starting Monday. Monday it starts, I think, 9:55 every class. No, it's not. It's in the afternoon on Monday and 9:55 on Wednesday. We will post the schedule. Okay, so should we review what we talked about last time? How about we review what we talked about last time? So last time, I gave you this program. This is the same program from last time. It is a for loop, some instructions, and we talked about we can compile this code, and we get out a list of instructions. And if I had a very, very simple processor, that very simple processor would just execute one instruction, and then the other, and then the other, and so on and so on. So one instruction per clock, simple processor. And then, okay, and then we talked about, well, wait a minute, maybe we can do better. Maybe we can make the code go faster. And we noticed something about the code. Now what we noticed was that even though it looks like a list of instructions, sometimes some of those instructions are independent. And if they're independent, we could execute them in parallel. So someone was asking a bunch of questions on the website. Who was that? Because you didn't put a name on the website. Ah, okay. So we had a conversation about instruction level parallelism. And the important part was that this program, some of the instructions are independent. The 3 multiplies can be done completely independently. Now that doesn't mean that they are done in parallel. Because if I ran this program with all of this independence on this processor, I don't have any ability to run in parallel at all. No parallelism. But this code can be parallelized. So we decided to build a new processor, still 1 core, but now 2 instructions at the same time, and 2 execution units to process those instructions at the same time. So here's a question. If I have this processor and this program, how long will it take to run this program on this processor? Okay, so 2 people say 3, so why do you say 3 units of time? How would you run the code?
X and Y is together.
So we can do these 2 instructions,
And
and then we can do these 2 instructions, and then we can do this instruction. So we've gone from 5 units of time, 5 clock cycles, down to 3 if we had this processor. Now what if I made a new processor? I don't have a picture, but what if I made a new processor and it had 3 yellow boxes and 3 orange boxes? How long would this program take if I had 3 orange boxes and 3 yellow boxes? Still 3, right? Because I could execute all of these, and then 1 of these, and then 1 of these. So this processor here, is 100% efficient. it's always doing as much as it can do. This processor is 100% efficient for the first clock, 100% efficient for the second clock, and only 50% efficient for the last one. And then if I had another processor with 3 instructions per clock, it would be 100% efficient, and then 33%, and then 33%. So this is a good example of why that graph, I don't have the graph anymore, but that graph, remember it got very flat. Because if I built processors that could find more and more instructions per clock, not very helpful anymore. Okay, so what did I say that would be a much easier way to run faster? It's a much simpler way for me to always get twice as fast. Because notice that we never even got twice as fast. We went from 5 instructions to 3. It was never 2x speed. So in many programs, computer graphics, computer vision, machine learning, scientific computation, you always have a lot of data to work on. And usually a lot of that data can be done in parallel or independent. So the idea that we talked about is we said, you know what, let's not do this for right now. This isn't always efficient. It's free because you don't have to change your program at all and your code got faster. But if you're willing to work harder and change your program, and you gave me 2 instruction streams now, you rewrote your program to create 2 threads. And with 2 threads, there are now 2 instruction streams. Then maybe I should build a different processor that only did 1 instruction per clock for every core. Well, maybe I build 2 completely separate cores, 2 very simple cores. And maybe they're a little bit slower. Maybe they're 75% slower or 60% slower, but I have 2 of them. And things are now faster. So you might be asking me, you might be wondering, how do I create 2 instruction streams in my program? I haven't shown you too much code for them. So what I decided to do is I wrote a program. And so here is my program. This is C++ 11. So, and the only thing that is C++ 11 is this right here. So this is void main. I have 1 instruction stream. Then at some point, I'm going to create a thread. And that thread is like saying, I want this thread to run in a new instruction stream. So if you look at this code, it creates a new thread. And you can look at the syntax yourself, but I'm passing this function to the thread. So when the thread starts running, it will start running this instruction. So this program has 1 thread, creates another thread, and then the first thread calls print hello. And the second thread, thread 1, calls print hello. So 2 threads call this function. And this function just prints hello from thread 0 or hello from thread 1. So here's my, I wrote that program right here. This is my program. I can compile that program. And now let me run it. So I'll run my 2-threaded program. So there's 2 threads and it prints hello. Well, when I change this program, I think my program prints hello 100 times. So it says hello from thread 1. So let's go back and look at what happened. So thread 0 was made. It's running. The first thing it did was create a new thread. And it takes a little while for that other thread to get running on the other processor. So it takes a little bit. So the first thread, thread 0, just started running print hello. Hello from thread 0, hello from thread 0, hello from thread 0. So that is printing. And then after some time, thread 1 is now running. So now there are 2 threads printing hello. So you see them interleave. So these are now running at the same time. And then you see thread 0 finishes. And then thread 1 finishes. So if I had to draw the picture of that, if I had to draw the picture, it would look more like this. So this is main thread. This is thread 1. And the main thread calls printf. This is thread 0. So let's go find that. This is thread 0. And then it launches thread 1. And so we'll say it launches thread 1, it creates thread 1, it spawns thread 1, and everybody uses different terms. So it takes a little while for thread 1 to get started. And for those of you that have taken an operating systems class, that's the operating system creating the thread. But it doesn't matter too much. So this thread starts running print hello. This thread starts running print hello. You see them on the console get interleaved. And then this thread waits for the second thread. So join says, like, if you think about this as splitting off a thread, you can think of join as bringing that back together. So it's like joining the picture. So when this thread calls join, it will wait. So thread 0 is called join. And join says, tell me when the other thread is done. So this entire time when thread 1 is printing, this thread is just stuck in this function. And when this thread completes, thread 1.join returns, and then main continues on. And you'll see the all done at the very end. Okay. So that's what I mean by creating an instruction stream. You'll use a library or a function call. You're going to tell the operating system, create a new sequence of instructions, run them in a new thread, and now those two instruction streams exist, and the operating system can tell the computer to run each of them on a different core. Question?
What happens if you don't join? Is it going to crash?
No, it'll be fine for now, but it would be bad. It's like not calling free at the end of the program.
What's the multi-data?
Multi-data? I'm not sure what you mean.
I mean, single stream. That's it.
Got it. Okay. 1 second. We will get there. So right now we've talked about one stream, one instruction stream, superscalar execution. That's the first part. Then I said, we can also make two instruction streams. Completely different instructions, but I had to change my program to tell the computer there were two instructions. Now if I have a computer with 4 cores, I could rewrite my program and create more threads. And I could run on this processor 4 times faster. Or I could change my program to make 16 threads, run on this processor. So that's that was one thing we talked about. So if I say multi-core parallelism, I'm referring to multiple instruction streams on multiple cores. This is a quad-core laptop. I can create 4 threads and get 4 times faster. It's easy. I don't want to talk about that yet, but there's actually only 4 cores. Okay, so the other thing we talked about is that we said, not only can I run different iterations of the loop in parallel, I can make new instruction streams. I can have thread 0 do I equals 0 to n divided by 2. Thread 1 do n over 2 to n. That's one way to do it. But I also observed, I said, wait a minute. All the threads are doing the same thing. Same instructions. They're all running the same loop. And so if I'm a hardware architect, my job is to be as efficient as possible. So one answer would be, well, if I want to run faster, I just go build more cores. I duplicate orange boxes and yellow boxes and blue boxes. But the orange boxes are what are responsible for processing the instruction stream. The yellow boxes do the work, but the orange boxes decode the instruction and figure out what to do next. So in a program like this, and many of our programs look like this if they were parallel, we have an optimization. We can say, you know what? I only need one orange box. I only need to be able to decode or interpret one instruction. But then I can send that instruction to 8 different yellow boxes, 8 different adders, 8 different multipliers. And all of them can run at the same time the same instruction on different pieces of data. And it turns out that this is a lot of transistors. And every one of these is a very small number of transistors. So it actually is quite efficient to share an instruction stream over multiple execution units. So if I do that, and let's say I have 8 execution units, every one instruction stream, one instruction, now does 8 things in parallel. So I don't have to create more threads. I have to write those SIMD vector instructions that I showed you last time. So I still have to change my program, but I change it in a very different way. Now I can combine these 2 things that we talked about last time. And I can build a new processor that has 16 cores, 16 instruction streams, but every one of those instructions is working on 8 pieces of data from the array. So now this processor has 16 cores, 16 instruction streams, but can do 128 things in parallel. So this laptop has 4 cores, has 8 wide SIMD instructions. And so given what I've told you so far, can actually do 32 things in parallel. So it's possible to take a piece of C code, and you will on assignment 1, and make it 32 times faster just on a little laptop, compared to what if you write in C. So this is what you should think about my laptop as. And even though we're talking about CPUs, all of these same ideas also are in GPUs as well, except there's just more cores and more SIMD. So if this is a picture of my laptop, this is a picture of an NVIDIA GPU. So you can think about it as 20 cores and basically 32 wide SIMD. And I'll talk about this more in a later lecture. But if this thing needed 32 pieces of data to run efficiently, and this thing needed 128 pieces of data to run efficiently, one of these things tends to need about 40,000 pieces of data to run efficiently. So it's like 40,000 small little instruction units. But I'll come back to that in a second. So that to me is what we talked about last time. So let's keep going because there's one more big idea in this lecture because we haven't talked at all about accessing memory. So let me go to what I wanted to talk about today. So today, So first of all, we have to talk about some terms. There's 2 terms that I need you to think about. The first one is memory latency. The next one is memory bandwidth. So you might have heard that memory is very slow. Memory is like having to drive somewhere to pick up an item at the store and bring it back to your house. It is that slow. So memory latency tells me how much time it takes for data to get from memory to the processor. So that's like me walking across the room. So the latency of me walking across the room is how much time it takes me to walk over here and then come back. That is the latency. The units of latency are seconds or clocks. Latency is an amount of time. If I want to reduce latency, what do I have to do? If I want to reduce the latency of me walking across the room, what do I have to do? I have to walk faster. Like if I don't have anything here. So let me see. So if I take Yan's phone, and he says, bring me my phone. Bring me my phone. The latency of that operation is how long it takes me to walk across the room. Okay? And if he is impatient, if he is unhappy with not having his phone, and he wants me to get it, if he wants to reduce the latency, we have two options. What are our two options? One is I walk faster. What is the other option? Well, I throw it to him. That's like walking faster. The other option is I stay right next to him. Right? So what is a cache in a processor? So everybody heard of a cache? You hear L1 cache, L2 cache. So if memory is really, really far away, and just to give you a number, in a modern Intel CPU, memory is about 200 cycles away. So if you say, give me this data from memory, the processor will not get that data for 200 cycles. I'm walking the data over to Yan. If the data is in cache, it might be 10 cycles or 3 cycles. And that's because cache is right here next to Yan. It's storage that's on the chip. So caches exist to reduce latency. So now let's talk about bandwidth. Bandwidth is the rate at which information can get to a particular location. So if, for example, let's say Yan had 100 phones. If he had 100 phones, I could carry maybe 1 or 2 phones over to him at a time. And if he was unsatisfied with that, if he wanted more phones, I would probably need to get more people to carry more phones. We would all have to walk at the same time. So if I got all of these people, we could give him all 100 of his phones immediately. Now, do more people reduce latency? No, because we all still walk at the same speed. So in computing, bandwidth would be like adding more wires, or making a wider bus, or building more highway lanes, right? So reducing the latency of me getting to downtown, I should buy a very fast car, right? If I wanted to increase how many people can get to the downtown at once, we should build more lanes to the highway. So that's the difference between latency and bandwidth. So on this CPU, we have a problem. So let's say we have an instruction which says load this data from memory, which is like saying, give me my phone to somebody across the room, or maybe deliver food to my house. Right? So if I want if I want the result of that operation, I have to wait a long time. And like I said, you may have to wait for hundreds or sometimes thousands of cycles for memory to get you to that data. So the first option not to wait is to build a cache. Is we put the data right next to the processor so that there's no waiting. But of course, only a little bit of data can fit next to the processor. Otherwise, we would never build memory. We would just build really big caches and everybody would go home. It's fine. It's easy. And so that is why this CPU has a cache. So it is not always waiting on memory. And it doesn't just have one cache, it has a whole bunch of caches. You know, it has one cache that might be 3 or 4 cycles away. It has another cache that's about 18 cycles away. This cache is about 30 cycles away. And then the memory is hundreds of cycles away. That's why we have caches. So caches reduce latency so that we never wait. The other thing that we could do, and it's more of an advanced topic, I will not talk about it anymore after this slide, is you could predict what data you need before you need to load it, and the processor can automatically load that for you before your program asks for it. So in the same way that a superscalar processor says, don't change the program, I'll figure out the parallelism for you. most modern computers have what is called a prefetcher. So it says a prefetcher because it's going to fetch the data from memory before your program runs the load instruction, because the processor is being very smart. So because of prefetching, sometimes you don't have to worry about latency on a CPU, because the prefetcher is pretty smart. But what happens if you have to go to memory? If you have to go to memory, my computer is waiting for a long time. So there's one other thing that we can do. And everybody does this all the time. And in computer science, we call it multithreading. So I should be a little careful. When I say multithreading right now, I really mean what we call hardware multithreading. And that the hardware has multiple threads. And I'll give you an example of this today. Today I did my laundry. I washed my clothes today. So I went to the laundry room and I put my clothes in the washer. And how many people think that when I pressed wash, I stood there and waited for 45 minutes for it to finish, and I did nothing else? That would be very wasteful, right? Nobody does that. So when you're doing your laundry, what do? You don't sit there and stare at it. What do you do instead? You go do your homework, you go eat food, you go do something else. And that is actually another form of parallelism, because you could do your laundry at the same time you were having dinner or doing your assignment. So when I say hardware multithreading, I'm talking about the processor doing exactly the same thing. So let me tell you how that will work. So I'm going to go back to the picture. Here is our processor. And it's a single instruction stream, 8 SIMD processor. And normally that processor can run one thread. It will run one thread per clock. Those threads may issue 8 wide vector instructions. So here's what I'm going to do. I'm not going to change anything in orange or yellow. But what I'm going to do is I'm going to give the processor a lot more registers. And really, this is where in the lecture I want to stop saying registers, and I'm going to start saying execution context. And I'll tell you why. Is that if I'm running a thread is executing instructions. And it says, multiply R0 times R1. So the value in all of those registers, and if you've taken other courses, value of other things like virtual memory, tape mappings and tables, or the program counter, every processor has to maintain information about how to run an instruction stream. The value of registers, what instruction to run next, maybe operating system information about the process. So I want you to think of the blue box as the data, the environment, the context in which a thread runs. So if I say hardware thread, I mean one blue box. So what I'm going to do now is I'm not changing anything, but I'm making multiple blue boxes. So in this case, I've decided to make 4 blue boxes. So you can think about there now being as 4 different R0s, or 4 different program counters. So there's 4 different states of 4 different threads. So now this processor has the ability to keep information about 4 threads on it all at once. Now notice that it can only execute the same as it did before. It can only execute one instruction. But now it might have 4 different threads that it can choose from when it wants to run an instruction. So let's think about how this thing will run. So what I'm drawing here again is time going down. This is a thread. And imagine the thread has 8 things in it because let's say it's all proper, very good vector code. So when that thread issues a load instruction, and this was my laptop, what happens here? What happens here? So can the processor do the next instruction yet? No, it cannot, because we have to wait 200 cycles for the data to come back in memory before we can do the next, we can add the data to something else. So normally, the processor would just completely stop. No progress, 200 cycles before memory finished its job. So think about that efficiency. We were unsatisfied earlier with 50% efficiency or 30% efficiency. Imagine if you did one load, one math operation. One load, one math operation. So you do one instruction, wait 200. One instruction, wait 200. That's 0.5% efficiency. It's very, very bad. That's why CPUs have caches, so you don't wait. But now, let's think about what I can do. This processor just put its laundry into the washer. But it has 4 other threads that could actually run. So what the processor does is it immediately switches and says, I will just start running thread 2 now. And so it immediately says, okay, while I'm waiting for that memory to get back to me, I will start running instructions from thread 2. And then when thread 2 does a memory access, thread 2 cannot run anymore, but I have thread 3. I'll go here, and I'll run a couple instructions from thread 3 until load, and then I stop, and then I do thread 4. And then, oops, thread 4 has a load, it can't make progress, and then what happens? Thread 1, at this point, thread 1 is actually ready to run. And so now the processor can run thread 1. So the important thing to keep in mind is that the registers, the data for all of these threads, is present on the chip so that the processor can make a decision almost every single clock about which thread to run. So for those of you that know about how operating systems work, operating systems do this all the time. We have way more threads. Let's look. If I go to activity monitor, I have currently 1,600 threads running on my computer, and I have 4 cores. So multi-threading is done by the operating system all the time. But the operating system is choosing which of the four of these 1,400 threads to put on the processor. If I have if I have a multi-threaded processor, like what I'm talking about now, the processor can actually put 4 cores times 4 threads all on the processor at once. So you said this processor was an 8-core processor. It's actually a 4-core processor with 2 blue boxes. So from software, if you type less proc CPU info and ask Linux how many cores, it will tell you 8 cores. But really what it means is it's like 8 virtual cores, logical cores. And those and on an Intel chip, every 2 of those logical cores share the same execution resource. So notice in this picture, what is my efficiency of my processor now? It is 100%, because if I look at any point in time, some thread is running. Someone. 100%. So it doesn't matter if memory takes a very long time. It doesn't matter if my laundry takes 45 minutes. I always have other things to go do. Now, so this is multi-threading is about efficiency, using the resources that we have. SIMD was about adding resources. Multi-core was about adding resources. So this is a major idea in this course, is that this multi-threading idea is the idea of I'm going to design a computer that only runs really well when there are a lot of software threads, a lot of different things for me to do. Because if we look at this one thread, if I go back to this picture, when does thread 1 finish? Thread 1 finishes here. If this was a single threaded processor, where would thread 1 have finished? It would have finished here. So one thread, any one thread is running slower because it is sharing the processor with 4 other threads. But overall, my processor is way more efficient because it's running at 100% efficiency, because I care about how long it takes me to finish all of the threads, not how long it takes me to finish one thread. So this is a trade-off. One thread will run slower. Just like when I got rid of all the fancy, out-of-order other stuff from the processor and made a bunch of small cores, one thread still got slower. So I keep making one thread slower to be much faster when I am running many threads. So there are some trade-offs here, because as you can imagine, there's only so much space on chip. So if I have a single-threaded processor, every thread gets a lot of registers, or maybe a big cache. If I want many threads, like what I just told you about, now they only can use a small number of registers. And I can maybe choose something in the middle, or something like that. So now I've created this processor that has all 3 ideas in it. It has 16 cores, it has 8 wide SIMD, and it has 4-way multi-threading per core. So if I wanted to run this program on this processor, I need 16 times 4 threads. I need 64 threads. So if I had to change my program, I would need 64 threads if I went back to the code I showed you, not 2. And if I want to use SIMD, I need 64 threads, and every thread is working on 8 pieces of data at once. So my array better be of length 512, otherwise I cannot run at 100% efficiency. Okay, any questions about this?
Yeah, that hardware multithreading, is that the so-called HyperThreading?
That is HyperThreading. HyperThreading is an advanced form of 2-way hardware multithreading. 2-thread hardware. And I have some comments online about how it's more advanced. A quick, well, no. We'll do it later. Okay, let me show you something that's very similar to HyperThreading. And so everything I told you about is true for CPUs. It's true for GPUs too. This is one core of an NVIDIA GPU. Same colors, same boxes, no differences, but just a lot more information. So every NVIDIA GPU has up to 64 hardware execution contexts. So if HyperThreading is 2, my picture before was 4, NVIDIA GPUs have 64 hardware threads. If you read the NVIDIA manual, they call hardware threads warps. So NVIDIA warp equals hardware thread in my lecture. Now every single one of those threads executes 32 wide vector instructions. So 32 SIMD. And then in my diagram before, my processor, every single clock, picked one of the 4 threads and ran one instruction from those 4 threads. An NVIDIA processor is a little bit different. It has 64 threads to choose from on every core. So what it does is every clock, it chooses 4 of the 64 threads to run. Not 1 of 4, but 4 of every 64. And from that 64, from those 4 threads, it will run one instruction that is 32 wide SIMD. So it can run 32 times 4, 128 math operations per core, per clock. And if you want to make things a little bit more complex, it is actually Superscalar. So out of those 4 threads, it can try and automatically find 2 instructions from those threads and run those too. So it can actually run up to 8 instructions per clock. So there's nothing very fancy here. It's all the same ideas. It's hardware multi-threading. So this is one core, 64 hardware threads. Every clock, pick 4 of them. Run one instruction from each of those 4 threads. That instruction is SIMD 32. And I'm not going to get into the details, but there's also Superscalar, so actually from every one of the 4 you can pick 2 instructions. That's the whole chip. Now, there's this picture, and it's also multi-core. Remember, there are 20 of these. So if you do the math, you have 64 threads times 32. So that is 2,000 pieces of data per core, all of that need to be running at once, times 20. So you cannot use an NVIDIA GPU unless your array is about 40,000 elements long. So you cannot be efficient without tens of thousands of parallel things to do. So so if the Intel CPU is saying a little bit of parallelism, the NVIDIA GPU uses all the same ideas, but says we will assume that we are only running things that have lots and lots of parallelism. And so they can be much faster when there's lots and lots of parallelism. But every single one of these threads is very slow, much slower than what's on my laptop. So this is why the CPU has all of these caches, because the CPU only has 2 threads. If the CPU stalls, there's only one other thread to do something at the same time. The NVIDIA GPU does not have big caches at all. Like Intel CPU has 20 megabyte cache. NVIDIA GPU, 2 megabyte cache. So the NVIDIA design assumes that you will always go to memory. And it will take a really long time. But who cares, because there are always many other things to do. So it's just a difference in design on what types of applications they want to run. So let's think about one thing. So given what you know, here's a question. And this question is very similar to something on homework. Imagine that we open MATLAB or something like that, and we want to add, or no, sorry, we want to multiply 2 really, really long arrays. Let's say that these arrays are 10 million elements. And I want to multiply every element of A times every element of B. Make sense? A sub 0 times B sub 0. A sub 1 times B sub 1. And I want to run this computation. Okay. So given what you know from the first couple lectures, how many think that this is a very good application for a modern parallel computer? And how many people think this is a very bad application for a modern parallel computer? Do you think this computation should be very efficient? Or do you think this computation should be very inefficient? So who thinks it should be efficient? Raise your hand if you're confident. So so these people think that it will be very efficient. So why do you think it will be very efficient? Lots of parallelism. It's the easiest thing to parallelize in the world. Okay. Not everybody raised their hand, so I want to know why. For those of you that did not raise your hand, were you shy? Or did you think that it was inefficient? Does anybody think it's inefficient? Yan thinks it's inefficient. Yan doesn't know how to parallelize things. It's very easy. No. Okay. So let's take a look. Let's figure it out. So let's think about how this program works. Every single time I do a multiply, there's 12 bytes of information. I have to load 4-byte floating point value A, 4-byte floating point value B, and I have to write the answer. 12 bytes. And this processor here, this one, the GPU, I can do 2,560 multiplies per clock, because it's 32 times 4 times 20. I have so many math units. So, it's okay. We'll take a break. And then we will look to see what I want you to think about the answer and see if anybody changes their answer in 5 minutes. Because the answer is that it's very, very inefficient. This is probably the worst workload you could ever have for a modern computer. And in 5 minutes, we'll talk about why. So let's see why this was so tricky. And this is a mistake that professionals make all the time. So let's go back to the math. My processor has 2,560 multiply units. It's a big GPU. To run that unit, to do a multiply, I have to load 8 bytes of information, 1 input, 1 output, and write 4 bytes of information. 1 input, 1 output. So let's say that my clock rate is, well, 1 gigahertz to make it easy. What is the throughput of the processor in multiplies per second? It is 2560 times 1 gigahertz. So it's 2.5 teraflops actually. So instructions per second is throughput. It's a measure of rate. So if I'm doing this many multiplies per second, I can compute how much bandwidth I need, which is 12 times this number. So if I take this number and I multiply it by 12, because every time I do a multiply, I need 12 bytes of bandwidth. And then I multiply it by 1.6 gigahertz, because that's actually the clock on the GTX 1080 GPU. That's the real clock speed. I get about 45 terabytes of bandwidth that I need to actually keep these math units busy. So the way to think about this is think about bandwidth of the memory as a big pipe of water. And think about the math units, the execution units, as the sink, the drain. And so in this case, the pipe is not big enough to keep the math units busy. So the math units will just wait. Or actually, a better way to think about it is think about the math units as this big pipe, and memory bandwidth as a little pipe. And so the big pipe will never be full because the little pipe is too small. And so I don't have 45 terabytes of bandwidth on any modern GPU. I have a lot of bandwidth, but not 45 terabytes. In fact, I have 320 gigabytes per second. That's a lot of bandwidth. But if I wanted to run this application at 100% efficiency, I need 45 terabytes of bandwidth. I only have 1% of the bandwidth that I actually need. So if you ran this application on a modern GPU, very parallel, 1% efficiency. Now it turns out that if we do the exact same calculation on my laptop, it turns out to be about the same actually. Because I have 3 gigahertz times 4 cores times 8 times 12, but I only have 76 gigabytes per second on my laptop. And it actually turns out to be about 3% efficiency. So should I run this computation on my laptop or on my GPU? So the people that are answering laptop, what is the reason why? It's more efficient. I make a better use out of my processor on the laptop. But which one is faster? The GPU is still faster because the GPU will give me the data at 320 gigabytes per second. Big pipe. The laptop only reads the data at 76 gigabytes per second. So if you wrote this computation and and then you ported it to the GPU, you would run, 4 times faster, 5 times faster. You'd be very happy with yourself. You're like, oh, it's because there's so much parallelism on the GPU. And you'd be wrong. The reason why it's faster is just because you bought a much more expensive memory system to run much faster. So we call this, in this whole class, we're probably going to think about throughput almost all of the time, not latency very much. Because we have so many other things to do. If we're doing millions of things, we can always hide the latency by doing something else. So what we care about when we think about is it efficient, we're saying, is this processor too fast for the memory? Or if it's a pipeline, is this processor faster than this processor? So we only think about throughput. And the best way to think about throughput is 2 pipes. So this is an example of, if I put a cache in my GPU, would it help? And I just told you the answer. The answer is no. But why would putting a cache in the GPU not help? Correct. I only read every element of A 1 time. I only read every element of B 1 time. I only write every element of C 1 time. So if I put a cache in there, every single data access would be a cache miss, because it would be the first time I was loading the data. So a fancy cache, and I give this question on an exam every year, and I ask people how to make it faster, and they always say, oh, change the code so it caches better. And there's nothing you can do here. This is pretty fundamental. Okay, so this was a situation of being bandwidth limited. And you will find in this course, I would not worry about the words on this slide, this is more for review, is that most of the things that you do will be writing good code so that you are not bandwidth limited. Nobody had to work very hard to parallelize that computation, but it was still 1% inefficient. Okay, so I'm going to move forward. These are slides that I put for review on the website. One thing that I think would be very good at this point is for people to just define on the website, go write a definition for all of these terms. These are the terms from the first 3 hours of the class so far. Okay? So I think before we move on to the next topic, I still want to go over this one more time. Okay? So go over it one more time. If you understand this, and I'm going to go fast, you understand everything that I've taught so far. Okay. So I have some code. I can run it on a processor. That processor can issue instructions 1 per clock. If I don't want to change the code and I want to run faster, I can build a fancy Superscalar processor that can run multiple instructions per clock. And if I actually look at this program, there actually are independent instructions. I can compute value independently from the numerator, independently from the denominator. Okay. I can rewrite this code and spawn an extra thread. If I spawn an extra thread, I can now use a multi-core processor. I took away the Superscalar for now. If I have a multi-core processor, I can certainly add Superscalar capabilities to each of the cores. So now I have 2 cores, 2 instruction streams. I can build 4 cores. Each of those cores, I can say, I will have the ability for you to run SIMD instructions. 4 cores, SIMD instructions. Okay? So now I need a program that is multi-threaded to use the 4 cores. I need a program that is vectorized, that's SIMD, to use the multi-threading. And I haven't even talked about this before, but it should make sense that I could have SIMD execution units and non-SIMD execution units, regular scalar ones, and my Superscalar could actually be finding 2 instructions, one SIMD, 1 regular. Same idea, just 2 different types of execution units. And if I do this, and I hook it all up to an L1 and L2 cache and an L3, what I have is basically a quad-core dual-issue processor. Oh, and I can add 2 execution contexts to it. And what do I have is I basically have my laptop now. 4 cores, 2 threads, 8 wide SIMD, and in fact, Superscalar to both regular SIMD units and traditional scalar units. So this is kind of a very cartoon, simplified version of modern x86. Okay. So, one more question. You write a C application that spawns 2 threads. We just did that in this class. You have this processor below. 2 cores, 2 threads per core. You are the operating system. You are Linux. You have to run 2 threads, and Linux gets to decide which thread runs in which blue box. So this is a 2-core processor, 4 logical cores, 4 virtual cores. So where do you assign thread 1? Which blue box? Doesn't matter, let's just pick this one. But where do you assign thread 2? Do you put it here, or do you put it here? What do you think? So, okay, so I heard 2 answers. So you said left. Why did you want to put it here? Okay, so you said that I want these 2 threads to be running on the same core, because maybe they'll share the same cache or something like that.
Yes.
So if this is a program where those 2 threads are touching the same data,
Yes.
that might be a good idea.
Yes.
And if I told you they were not touching the same data, what would you choose then?
Left and right.
So now you would put 1 thread here and 1 thread here. But why would you do that?
We can use different execution units.
Correct. So here, if I put 2 threads on this core, they are sharing the ability to decode instructions, the ability to run instructions. Putting multiple threads on the core is not about getting more resources. It is about using the resources on the core more efficiently. It's about avoiding stalls. So the only reason we have multiple threads on a core is to use the resources most efficiently. If we never stalled, we would never need multiple threads on a core. Very good. Okay. And then okay, so that's exactly right. The question is, who is responsible? Basically, when you create a thread, a P thread or a regular thread, it's the operating system that makes that decision. Just for those of you that know. So the answer is the operating system. Okay, and so I asked you that question. Okay, very good. I have some more slides that really help understand different ways to schedule threads. And you can look at those on your own. I never talk about that much. It's just review material. Okay, so let's talk about this homework now. Let's talk about what you need to learn for this homework. Okay. So in the last 30 minutes here, I want to talk, I'm going to talk concretely about how to program in a new program. But the real idea that I want you to keep in mind is the difference between an abstraction, or what is virtually true, and an implementation, which are the details of how things actually get implemented. So I'm going to give you one example for the next 30 minutes. But throughout this course, the biggest cause for confusion in most people is people confusing the abstraction with the implementation. Like, for example, a multi-threaded processor to software, to the operating system, is really 8 virtual cores. The implementation of those 8 cores could have been 8 different regular cores, or 4 two-way threaded cores. If we want to just think about 8 cores, that's completely fine most of the time, except when I answer the question about maybe what is the right way to schedule threads. Same thing will be true here. I'm always going to describe the abstraction first, and we often use the term semantics. Semantics are what the program means. The implementation is how it's actually scheduled. Another example would be an instruction stream. An instruction stream says that these instructions are always executed in this order. That is how we think about programs. The reality, the implementation, is that the processor can do whatever it wants as long as the results are the same as if they were executed in that way. So let's keep that in mind when we talk about this new language called ISPC. So ISPC stands for Intel's Single Program Multiple Data Compiler. Now ISPC is not a very popular programming language, but I use it because it's a very useful programming language to teach some of these ideas. And I think a lot of you may find it very handy for projects in the future. So the entire compiler is open source. So sometimes projects in the class actually are modify the compiler to improve it for some student project. We don't have projects in this class because we don't have enough time. But okay, so let's go back to this example. Again, same example because I don't want anybody to learn new code. And I'm going to rewrite it in ISPC. So this is plain old C code. This is a for loop. The semantics are, we run iteration 1, and then iteration 2, and then iteration 3, and so on, all in one thread. Okay. So I'm going to rewrite it now in ISPC. Now don't get scared. There's a lot of code on the slide. But most of this actually kind of makes sense. Is that the only thing I did is I took the loop and I put it in a function call now. Here's the call to sign X. And if you look at this, this is basically the same program as before, but there's some extra words that I highlighted in red. And don't worry about those words yet. So here's how I want you to think about an ISPC function. In a normal C program, you have a single thread of control. If you call a function, that thread of control starts running in that function. When the function returns, that thread of control starts running the caller again. An ISPC function's a little bit different now. So we're running the thread, and when we call sign X, this is ISPC code. So this isn't the ISPC language now. So this is this is C code, this is an ISPC function call. I want you to think about spawning a bunch of new instruction streams, or a bunch of new threads. It's kind of like the code that I showed you earlier that created a thread. But I want you to think of it as spawning a bunch of them all at once. Okay? So we get to here, we call ISPC signX function, and then we're going to have a bunch of threads run that same function. And then when all of the threads finish the function, we will continue after this running the same straight C code again. So this is kind of like spawning a bunch of threads. But I'm not going to use the term thread on purpose. I'm now going to use the terms that the ISPC language uses. Okay? So ISPC says that when we get to here, we don't spawn threads. They say that it spawns a set of program instances, which are kind of like threads. And specifically, they use the term gang of program instances instead of set. So I'm using their terms because if you read their documentation, I want it to be consistent. And there's a reason why they don't use the term thread, and I'll get back to that in a second. It has to do with the implementation. This will not be implemented with threads. So we get to here, we call sign X. Many instances of sign X start running. When all of those instances complete, sign X returns, and we go back to normal. So now let's look at the implementation of the code for those instances. So before, the code used to be for I equals 0, again, ignore all the red text for now. It used to be for I equals 0, I is less than n, I plus plus. Do all of this work. Now it's something slightly different. It's from I equals 0 to I is less than n, I plus equals program count. So program count is a special variable. program count is a variable whose value is the number of instances that got created. Okay? So in this case, let's just say it's 8. So if program count is 8, and this code loads the value of x at index, which is I, plus program index. Program index is a special variable, which says which instance is this actual logical thread of control. So I'm going to create 8 instances. The value of program count will be 8 for all of the instances. But for one of the instances, the value of program index will be 0. And for the other one, it will be 1 and 2. So it's basically thread ID. Program index is your thread ID. So given, now that you know everything you need to know, ignore the uniform word for now. Can you describe to me what this program computes? Well, really, what it computes is it computes the same answer as before. It computes the sign of every single number in the input array. But which instances compute which values? So I want you to think about it for a second. In fact, actually, this is a little trickier, so maybe you might want to talk to your friend for 30 seconds and figure it out. So talk to your friend, and I want to know how is it correct that this program computes every single output element? Because every instance does not. It only executes every program count element of the array. It skips over a bunch of them. So does everybody see how it works? Okay, so who sees how it works? How does this work? Somebody help me. Or in other words, if here's the picture, and here are the program instances. I only drew 4 of them for now because I ran out of space. And these are the elements of the array. Which elements of the array does instance 0 work on? Does it work on 0? Yes? And what else does it work on? Well, in this case, if there are only 4 instances, it would work on 4, 8, 12, 16, and so on, right? So every instance is working on every 4th or every program count number. Instance 1, if I look at the code, will be I equals 0 plus 1, and then I equals 4 plus 1. So it'll be 1, 5, 9, 13, instance 2, 2, 6, 10, and so on. So it'll look like, that. So this code, all of these instances in parallel, compute all of the elements of the array. So again, as a review, running code, create an entire gang of instances. Create 8 instances or more instances. Every instance runs the code that you saw on the screen. And the code that you saw on the screen says that, well, the code should run every 8th element. Okay, so the abstraction is up until now, if you wanted to think about this call right here as just spawning 8 threads, perfectly reasonable. You don't have to think about anything else. We know how threads run. It's like running 8 threads. They run in parallel. Good. That's not how ISPC is implemented. It is implemented with SIMD instructions. So what's going to happen now is that keep in mind that every single one of those instances is running the same program. So instead of compiling that code to instructions that run on integers or floating points, it's going to compile the code to vector SIMD instructions that run on 8 pieces of data at once. So even though I'm saying there are 8 instances, and it's perfectly reasonable for you to program thinking about there being 8 threads all doing different things, the actual implementation is that there's only one thread running 8 wide SIMD instructions. So there is no spawn of any threads at all here. It's running an instruction stream, sign X gets called, and then that thread just now starts running vector instructions for a while. So everything that I've shown you, this program only runs on one core, but uses the vector units without you having to write this nasty code. Just so you kind of understand. So I just rewrote the program now. So again, ignore the uniforms, but I changed how the index is computed. So talk to your friend again and figure out how this program is different. It computes the exact same thing, but does so differently. Different instances now compute different elements of the array. So talk about it for 1 second and see if you can figure it out. So now it says index for I equals 0 to less than count. And count is n over program count. So let's just assume program count is 4 or 8. Do you see what this program is doing? So how is it different? Which elements of the array does instant 0 compute? Yeah, well, it's not that it says 0 to 3. If n is really big, if n is a million,
0 to count minus.
yes, to count minus 1, but count is like n over 8 or n over 4. So now, instant 0, let's say n is 16. Instant 0 is going to work on consecutive elements from the array. And the next instance is going to run on the next set of elements from the array, and so on and so on. So the program computes the same thing. It's just now, instead of every instance like they're all interleaved, now they're blocked. They're chunked together. So here's an interesting question. Oops. Which one do you think is better? Two programs that compute the same thing. Which one's better? Okay, so I hear a lot of second ones. So why do you think the second one is better? You see a lot of contiguous data access, and that usually is good. But this is where you now have to think about the implementation. So the implementation are SIMD instructions. And this will be I think this will be a lot more clear once you start your homework, because you will actually implement the ISTC compiler. Not really, but you'll implement a very simple version of it. So let's think about what is happening, assuming that these are vector instructions. So here's a table. Here's iterations of the loop. This is the element that every instance is working on. So in the first version of the program, instance 0 worked on 0, 4, 8, 12, and so on. Instance 1, 1, 5, 3, 9, 0. But if these are implemented with SIMD instructions, that means all at the same time, all of these instances are working on contiguous elements from memory. So it actually turns out that the interleaved version of the program will run more efficiently because it can load contiguous data from memory and can use much more efficient SIMD instructions. Whereas if I change So here, that's really good. And if you want to go look at your Intel instruction manual, you'll realize that you can use a pack load instruction to do that all at once. If I change things to the blocked assignment, now all at once, so now everybody is contiguous within an instance, contiguous in time, but at the same time, it's now all separated apart. And I have to use a much more expensive gather, a much more complex instruction to get the data from memory. So it will not be nearly as fast. And you can write this code in ISPC and you can observe it. Right? So I turned what was a regular load instruction into a gather. Now, I showed you, like in this class, usually I'll show you how to do everything yourself. And then I'll show you an abstraction that makes it a little easier. So you often don't have to think about these things when you're programming ISPC. They give you a nice for each loop. And the for each loop means run all n of these iterations on whatever instances I created. Compiler, you make the decision, choose what's best. I don't want to think about it. Yeah?
Is that n plus 1 or?
Did I mess up?
It's
That is actually correct. The semantics would be 0 to n minus 1. Yeah. So in this case, if you wrote this code in ISPC, it is actually 100% equivalent to you manually making that code, the original version. That is its source-to-source transform. Okay, cool. So we did that, we did that, we did that. Yeah, okay. So this is a kind of interesting thing to think about. When you're reading ISPC code, you can think about it as every instance is a thread. And every thread has a thread ID. It just happens to be called program count. And every thread knows the total number of threads. It just happens to be called, every program count. And every thread has a thread ID that's called program index. But unlike most systems you've dealt with before, the compiler is not, there's no runtime creating threads. The compiler has compiled this code to send the instructions. So the number of instances is set at compile time. And so what would be a good number to set the number of instances for on this computer? You would use 8. So in fact, ISPC only allows you to use 4, 8, and 16 as the number of instances, because those are the vector instruction sets that we have these days. Okay. For those of you wondering, the reason why there's uniform here is because this actually tells ISPC that this code is the same values for every single instance. So what it can do is instead of generating vector instructions, it will generate scalar instructions, and those can actually superscalar dual issue with the vector instructions so you get better performance. So that's a very low-level implementation detail, but a good ISPC programmer will tell the compiler, this is the same data used by all instances. Like the denominator here is basically constant across all the instances. So the instructions generated can be much smarter. So it's not an important detail, but it's a good program. Okay, here's a question. If you understand this, you understand this, you understand everything you need to know. I don't think I would understand this right now either. But when you're practicing later over the weekend, see if you understand this question. So here's a piece of code. It's ISPC code. It says for every element of the input array, add it into this single variable sum. So sum is uniform, which means there's only one of them for all the instances. And then return the result. So this is basically like add up all the numbers in the array. All the instances are adding up all the numbers. This is actually invalid code. Is anybody thinking about why it's invalid? In fact, this won't even compile in ISPC. It will actually be a compile error. What I've created here is actually a race condition. Because I have all of these different instances. adding into a single shared variable and accumulating into it without any protection. So this is actually an invalid program. The way to write this in ISPC properly is to not make the value uniform. For each element in the array, add it into partial. So the way to read this code is that all of the instances are running iterations of the loop. Every time an instance runs the iteration, it accumulates into float partial, which is a per instance variable. So this is a partial sum. And then at the end, it combines all of the partial sums, all 8 of them, using a couple of special library functions which allow you to communicate across instances. So this reduce add is a special library function which adds up the 8 numbers, because there's 8 different partials and the 8 different instances. Reduce add will give you the sum of all of those. So if you understand why this is incorrect, and you understand why this is correct, you have a very good model in your head of how the code is, what the code means.
Do we have to say plus equals in that, or can we just say equals? Because it's per instance.
Correct, but this is, so this is, right, so this is why this is tricky. And ISPC is more of a research language. It's not a beautiful language at all. But since it's a research language, it's very useful to teach with because it's very low level. The semantics of this for loop are tricky. When I call the ISPC function, the parallelism starts here. Every single instance is running all of this code. And remember, it's running all of this code completely at the same time because that's the only way it can work. It's all 70 instructions. The semantics of for each is not parallelism. It just simply says there's a loop with n iterations. And I want to run all of the iterations exactly once. Compiler, you assign those iterations to the instances however you wish. So it would be valid, it would be correct, but inefficient for all of these iterations to be run by instance 0. But what will really happen is it will just divide them equally amongst all the 8 instances in the interleave fashion that we talked about. So every instance will do 1/8 of the work, or sorry, n over 8 iterations. So this partial is a per instance float. And every instance is just running its portion of the loop and accumulating new results into partial. That's why it's plus equals. And then at the end, there will be 8 copies of partial, which are the sum of 1/8 of all the elements in the array. And then I have to use some special library functions to add up all of those 8 partial sums. So that's why I said if you can actually explain to yourself what the program means, it hits about 8 different ideas, and you actually have a good command of ISPC. So when you're done with homework 1, hopefully this is no problem. Okay. So here's that code. Another way to think about this is what does it compile to? And the way this code compiles, remember it compiles the 70 instructions. So the instruction sequence will be the output of the compiler. I actually wrote my own version of it here with intrinsics. So let's look at that actually, because this will make a lot of sense. So here's my loop of, I want to sum up all n elements in X. So for I equals 0 to n, plus equals 8, I'm going to add a value out of memory, 8 elements from memory, into an 8 element vector that I'm storing right here. So there's one thread of control, right? One value here, which is a vector of 8 floating point numbers. They all start out as 0. So this says, put 0 in all elements of this vector of 8 numbers. This is just really low-level nasty code. So now I have a vector of 8 numbers. For I equals 0 to n, skipping 8 elements at a time, load 8 elements from memory, add those 8 elements to my local variable. So now I have a new updated value of partial, which has 8 numbers. Plus equals 8, because I'm skipping by 8 elements every time. And then at the end, I just have a normal, regular C loop, which says for I equals 0 to 8, add up all of the elements in partial to get the total result. So notice how this is one thread of C code running vector instructions. This is exactly what this will compile to. So this for loop says that we're going to do n things, but we're going to partition them across the 8 instances, which you can think of if you want to talk about implementation as across the 8 vector lanes. We will do that sequentially, and then we'll combine the results at the end. Okay, so I think that that's all I wanted to talk about today. I just want to review this. We call this the single program multiple data execution model. Really, it should be called single function multiple data. It would be much clearer, actually. So SPMD is single program multiple data. In ISPC, it's really you write one function, and we're going to run that function 8 times, equivalent to 8 vector lanes. And the data that's loaded into those vector lanes is derived from whatever your program index is, whatever your instance ID is. So every one of the lanes, every one of the instances will be operating usually on right next to each other data. And that's why it's so efficient. So single thread of control, vector instructions for here, but logically, multiple threads of control here. And then back to single thread of control here. I'm not going to talk about it. You'll deal with it in your homework. ISPC does have a way to create multiple threads that run on multiple cores. Everything I talked about in this lecture was all one thread on one core. So you will deal with that in your homework. Okay, so I think that's everything that I wanted to talk about. So I can, in the last couple of minutes, I can take any questions, or I can answer questions in the summer class, or people can go because it's hot, and I can answer questions here too without raising. All right, very good.